Welcome to Calculus. Today we will investigate calculating area under curves by limits. Let's take a look at one example. Here we want to consider the function f of x equals x cubed plus 5 over the interval from x equals 0 to x equals 2. Just to help us visualize what this kind of slice of the function looks like, let's just bring a graph here. So I've graphed this using a graphing calculator, and notice that we have just part of that cubic function. So just to visualize what we're trying to accomplish with this task is we want to calculate the area underneath this curve, so between the curve and the x-axis. Now we've used different techniques with this same function in previous lessons with rectangles either having their left endpoint on the function, their midpoint on the function, or their right endpoint on the function. And then we improved that by looking at trapezoids to get a better estimation. And what we're up to now is really a more and more exact calculation of the area under this curve. So again, just to visualize, we are trying to calculate the area of this slice underneath the x cubed plus 5 function. Well, we want to do this departing from the idea of a Riemann sum or a trapezoidal sum, where we really increase the number of rectangles underneath this curve from really n rectangles, so that would be discrete, up to an infinity. We want to think about having infinite rectangles underneath this curve. And the way that we're going to accomplish that is through the limiting process of a summation. So let's start by describing how we want to represent these rectangles first. So we'll just start by saying what the width of each rectangle is going to be. We'll call this delta x. So we are thinking width in terms of the x dimension. And the way that we're going to calculate delta x is using the formula b minus a over n. Now the b and the a are the two extremes on this interval. So I'll label them. Our a is going to be 0, our b is going to be 2. So we can actually calculate what this is going to be. It's 2 minus 0 over n, which is just going to be 2 over n. Again, what we mean by the variable n is how many rectangles we're going to create. So up till now we've had, for instance, 4 rectangles, so our n value would have been 4. But notice we're leaving it general here because ultimately I want to take that number up to infinity. Well, that's the width. What we also need to describe is the height of each rectangle. Now that's determined by really the function value, because we're calculating the area from the x-axis up to the function. So when I think about the height of each rectangle, it's really going to be governed by the function. So I'm going to call it f at c sub I. Now c sub I we haven't defined yet, but let's do so using our width expression. So c sub I is really taking the a value and adding to it the index I times delta x. And essentially this helps us to kind of partition that entire interval from 0 to 2 into rectangles. So for us, the way that we'll define our c sub I is going to be as a, which is for us 0. We start at the x value of 0, plus our index, times what we've already defined as our delta x, or our width, which is 2 over n. So that's going to simply reduce to 2i over n. So for us, the the f at ci that we want to calculate is going to be given as f at 2i over n. And so to define the height, I just need to plug in this x value of the rectangles across the interval from 0 to 2 into the function. So that's going to be the variable x replaced with 2i over n to the power of 3 plus 5. So that defines our width, that defines our height. And what we need to set up now is really how we're going to calculate the summation. So definitely we're going to have to multiply height and width of each rectangle. But then I also want to add up all those areas of the rectangles. And so this is how we want to set it up. Let's define it as the integral. So we'll say this is the integral from 0 to 2 of our function. So our function again is x cubed plus 5 times what we'll call delta x here in the interval is, or in the integral is dx. So that's the formal integral notation. But again, we're trying to calculate this using the limiting process. And that goes to really the definition of the integral. So we'll set this up as the limit as the number of my rectangles goes to infinity. So you can imagine as our number of rectangles increase, their width is going to get smaller and smaller and smaller till they're really just slices that we're adding up. So we do have to add them up. So I want to put the summation notation. And we'll go from an I value of 1, which would be my first rectangle, up to my nth rectangle. So really that's the way we're partitioning that interval from 0 to 2. And the way that I want to create my summations is really the height times the width. So the height that we already established is this 2i over n cubed plus 5. And what we're going to multiply that by is our delta x, which we've identified as representing our width. So that's 2 over n. And that is really, in very condensed form, the way that we want to calculate the area under this curve. So what our task is now is to really simplify the limit of the summation. So the first thing that we want to do is pass delta x outside of the summation, but keeping it inside the limit. So delta x, just to identify that factor here, is again 2 over n. So what we're going to do is let it pass outside the summation, but it needs to stay within the limit. Again, it can pass out because it doesn't involve an I, but it does involve an n. So that is really under the governance of the limit still. So our next step is going to be the limit as n goes to infinity of 2 over n. So that's where our delta x has passed outside the summation. And what that leaves is still our summation from I equals 1 to n of this height expression. So I do want to cube that. That's going to be 8i cubed over n cubed plus 5. So at this point, what we want to do is distribute the summation. And essentially the summation, what we'll do is we'll carry with it the delta x. We want to distribute it to each of these terms that are parts of the height expression. So our next step here in this calculation using the limit is the limit as n approaches infinity of 2 over n times the summation from I equals 1 to n of, first of all, 8i cubed over n cubed. And then we'll also have another term here plus delta x, which is 2 over n times the summation from I equals 1 to n of 5. So what we've done there is distributed the summation to each of the terms within the height expression. Now what our goal is we want to extract, factor out from each of these two summations any constant multipliers and also any powers of n. So my next step, I'm going to factor out here. So we'll investigate this first term to begin. So I got 2n there, but I want to bring out the 8, and I also want to factor out the n cubed. So both of those are going to exit the summation, and we'll multiply them with the delta x out there. So what we'll have is limit as n approaches infinity of 2 times 8, that's 16, over n to the first times n cubed, that's n to the power of 4. And now notice all that's left in terms of the summation from I equals 1 to n is I cubed. Okay, we want to do this a similar factoring out of the second term here in the summation. So all we got there's a constant 5. I do want to bring that out by factoring it out. So it's going to multiply times the 2 in the numerator of delta x. So that's plus 2 times 5 is 10 over n times the summation from I equals 1 to n of 1. Now at this point, once we've isolated the summation from I equals 1 to n of a power of I, let's highlight where we're looking here. It's really this component right here in that first term. We have some established rules, so I want to make a substitution using one of these established power sums rules. Let's go ahead and record what those are. So there's really 3 of them that we'll need potentially for calculating the integral using this limiting process. So the power sums would involve different powers of our index I. So let's just consider that summation from I equals 1 to n of simply I to the first power. So the rule that we can use for that one is given by this expression. It's a fraction n times n plus 1, all divided by 2. So that's not one we'll need. We're really after I to the power of 3. But again, I want to give these power sums so that you have access to them. We would also consider the summation from I equals 1 to n of I squared. And again, that's given by the expression n times n plus 1 times 2n plus 1 all over 6. So again, that's not the one we need. It's good to have though for other functions, other polynomial functions. And here's the one that we're going to need. It's the summation from I equals 1 to n of I cubed. So the rule that is established for that summation is n squared times n plus 1 quantity squared, all divided by 4. So again, those are just established rules, and we just want to select whichever ones apply for substitution. So the one that we want is definitely given by this third expression, the summation from I equals 1 to n of I cubed. So we want to make a substitution in our limit. So our next step is going to be the limit as n approaches infinity of 16 over n to the power of 4. So that part didn't change. But now I'm going to substitute in this identity, which is n squared times n plus 1 squared over 4. And then for this second summation, I've got 10 over n, and all that I've got there is the constant 1. So if I'm having I from a summation from I equals 1 to n of just 1, that's going to turn into n. There's going to be n rectangles there that I'm adding up. So notice we're we're done with the summation. So now what we're looking at is really just the limit portion of that expression. So for my next step, what I want to do is simplify, and I want to combine these these multiplied fractions. I won't combine the sums, but let's simplify the products. So the limit again is from n to infinity, headed to infinity. And what I noticed from this first multiplication, I got a 16 in numerator, 4 in denominator. So that's going to become, well, in fact, what we'll do is let's just merge those two fractions for a moment. So we'll just look at it like this: 16n squared times n plus 1 squared over 4n to the power of 4. And from our second multiplication, 10 over n times n is going to be 10n over n. And now what I want to do is make some cancellations if possible. So still we're looking at the limit as n approaches infinity. So within that first fraction, what I can cancel is going to be 16 divided by 4. That's going to leave 4 in my numerator times, I also have a cancellation in my n powers. So n squared is above, n to the 4th is below. So that entire n squared is going to cancel. And this is going to just leave n plus 1 squared over, all that's left in my denominator is n squared. And then for my second fraction, all I have is 10. My n's will cancel. So at that point, we're really ready to calculate the limit. So we just need to reason through this. So the limit as n goes to infinity of 4 quantity n plus 1 squared over n squared. What I notice here is that my powers on n, in the numerator, it's going to be n squared. In the denominator, it's also n squared. And so the idea is I take that out to infinity, they will cancel, and all I'm left with in terms of the limit is that coefficient 4. So this is going to equal 4 plus, and then the limit as n goes to infinity of 10 is simply 10, and 4 plus 10 is 14 units square. Again, what we're calculating is that area under the curve. So that is an exact calculation. It's not an estimation. So just to compare it with our estimations, again, which were the Riemann sums with the different places where the rectangle would hit the function, either at the left endpoint, the right endpoint, or the midpoint of the rectangle, or the trapezoidal. Let's compare. So we know that the area is now 14. Let's just take a look back at our estimates. So the right Riemann sum, which we had identified as an overestimate, calculated as 16 1/4. So definitely it's an overestimate. If the actual value is 14, it's over by 2.25. The left Riemann sum clearly underestimate. We saw it when we were drawing the rectangles. There's empty space underneath the curve, between the curve and the rectangles. So 12.25, 1.75 lower than the actual area. Midpoint Riemann sum was really close to the actual area, 13.875. So just a matter of 0.125 away from the actual value. Which surprisingly enough is a closer approximation than the trapezoidal sum. Trapezoidal was calculated as 14 1/4, so that is a distance of 0.25 away, which is farther than our midpoint Riemann sum. So it is good to just take kind of a look retrospectively and see which one of our approximations is the closest to the actual calculation. In this case, it would have been the midpoint Riemann sum. Well, thank you for joining for this investigation of calculating area under curves using limits and summations. See you soon.